G'day and welcome to this third video on Babylonian differencing techniques and polynomials, and I trust you enjoy what you're about to see here. If you haven't already seen the previous two videos, I would encourage you to do so, either before or after this one, but it will give context to what I'm about to share. What we're going to do in this video is look not at polynomials, which is what the differencing technique is designed to do, but instead to look at power functions, exponentials. So here we go, exponential functions. And this opens up something new and exciting. Let's imagine I have an equation like 2 to the power x, and we'll draw up a table of values. X and y, we'll start with 0 and we'll go 1, 2, 3, well, let's go to 4. I encourage you to explore these, make up your own exponentials, add 1, multiply it, put a 3 out the front or something. Try out a variety of these, but this is the process. I've chosen a particularly simple one here. If x is 0, 2 to the power 0 is always 1. Anything to the power 0 is 1, except 0 to the 0, and there's a debate. 2 to the power 1 is 2, 2 to the power 2 is 4, 2 cubed is 8, 16, 32, 64, 128 and so forth. Let's look at the differences. The gap here is 1. The gap here is 2. The gap here is 4. The gap here is 8. It's interesting. What are the gaps? The gap here is 1. The gap here is 2. The gap here is 4. The next one will be 8. If we look at the gaps, I think you can see what's happening, can't you? In the previous videos we saw that if we analyse a polynomial, like a quadratic equation or a linear equation or a cubic equation, that there comes a row when all these numbers are identical. Absolutely identical. For example, if it was a quadratic, on the second row, because a quadratic is something squared to the power 2, and on the second row we might find we've got a 2, 2, 2, 2, whatever. But here you can see this will never stop. This would be an 8. And the differences will continue like this all the time. So whenever we have an exponential function, we start finding a repeated pattern. Always looks the same. Now this doesn't help us find what the exponential is, but that's the pattern that exponentials produce. So at least it helps us recognise one. Does that make sense? Well, I'm going to show you something I discovered when I was at school. I'll get rid of these. Like all school discoveries, I was so ecstatic when I found it. I thought I'd solved something no one had ever seen before. Well, I sort of knew people would have. And years later, of course, I found it in books and things. But at the time, this sense of discovery was exciting. What I did was I decided, since I read about the differencing technique, and by the way, I've done it in the previous two videos. Let me plug this book. It's not my book. This is a book that revolutionised mathematics for me when I was 15 years old at school, and I stumbled upon it in my little country town in a news agency. Don't ask me how or why. I never got to ask the news agent, but in amongst all the novels and romances and whatever, there was a mathematics book sitting there. Just one. And this was it, The Search for Pattern by W.W. Sawyer. And I flicked through it. I thought, that's odd. And I flicked through it and I saw diagrams and patterns and things. I thought, oh, that looks interesting. I bought it for $1.35 and I took it home and read it from cover to cover. I still have all the original marks in it. It absolutely turned my mathematical world upside down. School mathematics textbooks are boring. This wasn't. This just opened up whole new vistas for me. And let me recommend any of the books written by Sawyer. Fabulous stuff. And that's where I learned about this differencing technique, and I started applying it to all sorts of things, even knowing that it's really designed to analyse polynomials. But I decided to analyse the Fibonacci sequence. 1, 1, 2, 3, 5, 8, 13, 21, 34, and so forth. Where the next term is the sum of the previous two terms. 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, and so forth. Well, let's look at the differences. I want you to see something. Difference here is 0. Difference here between 1 and 2 is 1. Between 2 and 3 is 1. Between 3 and 5 is 2. 5 and 8 is 3. Between 8 and 13 is 5. And if we look at the differences again, this will be 1. Don't worry about that. Don't worry about that. But look, difference 1, 1, 2, 3, 5. The same pattern. And if you look at that, you think, if I'm getting the same pattern with some extra stuff, but the same pattern, row after row after row, that's what an exponential looks like. And I thought, this means that the Fibonacci sequence must behave like an exponential. Well, it makes sense because the ratio of terms, 5 divided by 3, 8 divided by 5, 13 divided by 8, and so on, as you progress down the sequence, gets closer and closer to the golden ratio of the Greeks. And therefore that becomes the common ratio of the term of the sequence. And I thought, we have an exponential here. And consequently, I tried to make up an equation for the nth term. Oh, here we go, the xth term. And since we're using y, let's change this to t for the term. So what's the xth term look like? Well, I said it's probably something to the power x. And what I'll do is I'll chuck another number in front, just in case there's a coefficient. But I know it's not pure like that, because, well, for starters we get whole numbers, but also when you see how it converges on the golden mean, sometimes it's above, then below, and above and below, and above and below. So I knew there was another term going plus minus, so I thought what I'll do is I'll put another exponential after it. And this now has 4 unknowns, A, B, C and D. Really doesn't matter which way around they are. There we go. Well, all I did was then I substituted 0, 1, 2 and 3 to get 4 equations with 4 unknowns and solve them simultaneously. And I encourage you to go through the process. And what I learned was that there is a formula for the nth term of a Fibonacci sequence. I suppose I could call it F for Fibonacci, couldn't I? And the formula, it turned out this coefficient was the same. It was 1 on root 5. And it turned out that the other two terms, one was 1 plus root 5 on 2, which was the golden ratio, and the other was 1 minus root 5 on 2. And because that's negative, because root 5 is bigger than 1, as the power switches between odd and even powers, sometimes it adds, sometimes it subtracts. And that's how we get the jumping effect with the Fibonacci sequence. Here's a formula for the nth term of the Fibonacci sequence. And I stumbled upon it because this difference in technique showed that I was dealing with an exponential, a power, because of this constant repetition. And you might analyse a problem if you're doing research in science, or if you're just researching something you've discovered in a book or something you've experimented with. And if you see if you use the Babylonian differencing technique, 3,000-year-old technique, and you're seeing a repeating pattern, you, my friend, are dealing with an exponential function of some sort. And I encourage you to track it down. So, a repeating pattern on one line means you're dealing with a polynomial, but a repeating pattern forever and ever, exponential. How fabulous is this? 3,000-year-old mathematics still vibrant and helping us today. If you've enjoyed this, please like the video and please leave a comment. I very much appreciate them. If you're not a subscriber, then I encourage you to subscribe so you can find out about future videos. And I thank you again for watching.